In this presentation, we will be focusing on the fundamentals and working of the impedance track algorithm. The impedance track gauging algorithm incorporates both voltage correlation as well as Coulomb counting. It acts as a voltage-based gauge under no load conditions and as a Coulomb counting gauge under load. As the name impedance track suggests, the algorithm updates impedance in real time along with computing the remaining runtime and state of health. The algorithm uses impedance, discharge rate, and temperature in a simulation to calculate the usable capacity, also known as FCC, which stands for full charge capacity. In the figure, QUs is the FCC. The battery impedance strongly depends on temperature. The plot on the left shows how the battery impedance increases with decrease in temperature, particularly towards the end of discharge, say around 70 to 80% DOD, where the effect of temperature is more pronounced. Plot on the right shows the voltage profiles at different temperatures, where you can see that there is a larger IR drop at low temperatures due to the larger resistance value. As a result, at low temperatures, the voltage reaches the terminate voltage earlier compared to that at room temperature, and hence the available capacity is reduced. Therefore, in order to obtain accurate gauging performance at different temperature conditions, particularly at cold temperature, it is important to model the impedance as a function of temperature. Not just temperature, age also has a strong impact on battery impedance. From the plot on the left, you can see that the impedance, the low frequency or DC impedance in which we are interested, increases with cycle. Impedance doubles after approximately 100 cycles. As the battery impedance increases with age or cycle, the available battery capacity also decreases with cycle, as can be seen on the plot on the right. Therefore, it is extremely important to update the battery impedance with age for accurate gauging. What are some of the main features of the impedance track algorithm? One of the integral components are the battery chemistry tables, the OCV and resistance obtained from the ChemID and stored in the data flash of the gauge. The algorithm also consists of update of impedance and the maximum chemical capacity Qmax to account for battery aging. Last but not the least, periodic simulations are run to update capacity based on different conditions such as load and temperature change. The open circuit voltage OCV can be considered as the signature of a battery determined by its cathode chemistry. OCV profiles can be very consistent if the base cathode chemistry is the same, such as lithium cobalt oxide, lithium iron phosphate, etc. OCV of a battery can be measured after the voltage has fully relaxed. Using this OCV value, DOD can be obtained via voltage correlation. DOD is obtained from two consecutive relaxation periods, and the Coulomb counter charge between them is required to update Qmax. Qmax is computed as the past charge divided by the difference in the two DOD points. It is important to update Qmax because Qmax decreases with age. Qmax value reduces by around 3 to 5% after 100 cycles. As we saw before, it is important to update impedance since impedance changes with age and can affect the gauging accuracy. Resistance is measured real-time as OCV minus an average battery voltage divided by the average current. The simulation is the engine behind the impedance track algorithm used to predict the remaining available capacity. The simulation runs under certain conditions such as significant change in temperature, Qmax update, or if the DOD crosses a resistance DOD grid point during discharge. Here, Q start is the amount of charge between DOD at EOC and DOD 0, where DOD at EOC is the DOD computed at the end of charge, and DOD 0 is the last DOD computed using OCV correlation. Past charge is the coulombs counted after DOD 0 was computed. The full charge capacity FCC is then computed as the sum of Q start plus past charge plus remaining capacity. In summary, using an impedance track gauge has many advantages. The algorithm is able to handle dynamic conditions such as load and temperature variation, which is made possible by accurate battery modeling. The algorithm also has the ability to adjust for changes in usable capacity due to cell aging. A lower terminate voltage can be used, thereby increasing the battery runtime. It gives you the most flexibility to handle any kind of conditions, any kind of cells, any kind of systems by tweaking certain knobs in the flash memory of the gauge, and it saves your host from needing to do any kind of complicated gauging algorithm.